Thanks for joining us today in our webinar about automating viscous meshing for a transonic aircraft model using Glyph scripting. My name is Chris Sidoroff, and I'll be joined by Travis Carrigan, who'll be driving the demo here in a few minutes. So let's get into it. So really what scripting is about is trying to reduce the meshing effort. So just a clarification here, when we talk about, I mentioned in the last slide in the title of the webinar, we talked about automating that meshing process. Here at Pointwise, we're pretty careful to distinguish between automating something versus making it automatic. And the reason we choose not to use the word automatic is because what happens when an automatic process breaks? The user has very little or no control in that process, and so if it doesn't work or gives less than optimal results, there's often little recourse, and it just usually just go back and restart the process, which can be time consuming if this has to happen many times. So what we try to do is give the user lots of useful tools, and then provide methods for automating those useful tools. So what we're trying to automate is manual, tedious processes in the mesh generation step. So we can think of that maybe on two ends of the spectrum. We can think about things like specialized tasks. A very simple one is just maybe you have your own custom point distribution function you want to use that's not available in the Pointwise GUI. Or, for example, maybe you've developed some particular process that's specialized to your company and the application you work on. And then at the other end of the spectrum is automating the entire mesh generation process. And maybe an obvious example of trying to do that is in a design optimization loop, where the CFD solver and the optimization software are driving the parameter input for the actual mesh generation itself. So just a kind of a quick rule of thumb that we use here when it comes to scripting and deciding when to actually spend the time to write a script is that if you plan on using the same geometry for more than about 3 or 4 grids, and it's probably a good idea and probably worthwhile to think about trying to automate that process through scripting. So when I talk about automation, there's lots of different ways that you can automate things in Pointwise. So we're here to talk about scripting today, but there actually is some built-in automation tools that I'll just kind of describe really briefly here. We have like undo and redo in Pointwise. For those who are familiar with GridGen, assembling domains and blocks can be a very tedious process in Pointwise that can be automated. There's customizable toolbars, so you can put your most commonly used functions right on the toolbar, accessible at one click. All sorts of keyboard accelerators, and then journaling, where you can actually record the output of the scripting language that you're actually doing in the GUI to help you learn about and build scripts. So when it comes to scripting, there's 2 ways you can do it. You can do it interactively, or you can do it in batch. So interactively, you can automate the entire mesh generation process, but you can run that script in the GUI. That's fine. I talked about encapsulating repetitive tasks, maybe standardizing, a particular method for creating your grids for your analysis process. And the other one, like I mentioned before, maybe your company's developed some sort of proprietary knowledge, so you want to do that in some sort of script that you keep to your own processes. And then batch scripts that's where you don't even see the Pointwise GUI. You're running it totally in batch, driven by some sort of input file with some parameters in it. So again, this is automating the entire process, integrating it into some sort of analysis process or optimization loop. So and then on the right here, just an image of a script that we have available for Pointwise. It's an automated centrifugal pump meshing script, and this one actually has a customized GUI built into it for doing that. So the application we're going to be talking about today is from the 4th AIAA Drag Prediction Workshop. It's a simplified transonic wing body tail aircraft called the NASA Common Research Model. And specifically within that workshop, one of the pieces of it was a grid convergence study where they're looking at the effects of, obviously, the grid and its effect on the drags. And so that's what the script that we're going to be demoing today is going to be concerned with, is being able to create the family of grids that's necessary for a grid convergence study, because essentially we just want to look at the effect of the increase in resolution while trying to maintain the same or very similar character throughout throughout the increasing resolution of grids. So Glyph is the name of our scripting language. So Glyph is based off of the publicly available TK programming language. So we didn't invent a new language. We're just building off an existing, well-documented, robust language. But maybe more importantly for you is that Glyph, or actually, Glyph, the scripting language, was designed into Pointwise. So Pointwise was designed in mind with scripting from the beginning. And in fact, Pointwise runs in two threads. There's a core where all the computations and calculations are done, and then there's a GUI where which you interact with, and those two threads actually communicate through the scripting language. And so that's the benefit to you, is that everything you can do in the GUI you can do in Glyph, and so you're essentially just intercepting those commands and then sending them straight to the core. A little bit about just the kind of general philosophy about Glyph. It tries to mimic the GUI's noun-verb paradigm. For those of you who aren't familiar with the noun-verb paradigm, and the Pointwise GUI, the process for creating doing operations is to create an instance of an entity or an object first. That's your noun, and then once that's created, then you go and modify it or manipulate it. And so you apply some sort of action or method to that instance or object. The nice thing about this, the GUI's noun-verb paradigm, and it kind of closely follows the object-oriented methodology that's become ubiquitous for lots of modern programming languages. And so we've tried to incorporate that object-oriented methodology into Glyph, where we have classes that allow you to create instances of those classes, and then there's methods that allow you to operate on. So it's again the noun-verb paradigm in Glyph as well. So just to kind of show you that what I mean when I talk about that, so here's just a snippet from the Glyph man pages for the structured domain class. So first of all, that structured domain class inherits methods from higher level classes, so inherits the methods from the domain class, the grid entity class, and so on. But itself has its own class methods that only work with itself. And so, and again, these class methods are for creating an instance of this class. We can also apply defaults for when we go to create an instance of these class. And then the last one, the instant methods. Now these are the verbs. These are the actions that we need to call to actually modify or manipulate an instance of that class itself. And a little bit about where you can go to find more information about Glyph. We have there's two big sources of reference. We have the man pages, which I just showed you a snippet from. That's available. The link to that's available through the help menu in Pointwise. It'll take you straight to our website. And also there's a reference manual, which is a PDF document provided with the Pointwise installation, and that kind of gives a higher level overview of what Glyph is, and gives you some examples and talks a little bit about, it gives you an introduction to Tickle itself. So with that, Tickle, I'm not going to explain it too much other than the fact that it's a very mature, very well documented dynamic programming language. Tickle also comes with a GUI toolkit called TK. So like I showed you a few slides earlier, you can write your own custom interfaces, and you can leverage that straight in Pointwise. And Travis is actually going to give you a small sample of a TK GUI running a script. So there's a large body of documentation and learning material available on the internet. So the internet is definitely a great resource for learning about Tickle and TK. So with that, I'm about ready to pass it over to Travis. This is just a kind of a flow diagram describing the process for creating the script and creating the mesh. One thing I want to say before I pass things over to him is that that there's no way we'd actually be able to show you how to write this script line for line in the time allotted for this webinar, and then probably quite frankly be probably pretty boring just to watch us do that. So what we're going to do, the kind of the process here is that we're going to kind of drive the script in the GUI to kind of show you what's going on visually, and then Travis is going to hop over to to the important sections in the script to highlight and talk about some of the glyphs constructs. So with that, I'm going to pass things over to Travis.
All right, thanks, Chris. So this is the scripting process, the 6 steps of the scripting process that I'll be covering today. And like Chris mentioned, the way this is going to work is I'm going to demonstrate them in Pointwise by running the script. And the idea is to basically show the similarities between the noun-verb paradigm in Pointwise that Chris was talking about and the object-oriented methodology in Glyph. So with that, I'm going to start talking about initialization. So I'll just minimize PowerPoint here and execute our script. So like Chris said, Glyph is basically an extension of the Tcl programming language, and it comes pre-packaged with TK, which is a GUI toolkit, so you can build your own custom user interfaces like the one I'm showing here. You can launch them straight within Pointwise, and they can be used to drive your script. So this TK GUI is basically going to allow me to step through those 6 steps in the scripting process. So the first one is initialization. So really the first thing that happens during initialization is it's going to load in the geometry, the NASA Common Research Model. And you can see it's loaded in the geometry. It's a watertight solid model made up of a number of quilts that we've actually named. So we've named like the wing and the tail quilts. The idea here is so we can go and retrieve those when we begin modifying and refining the mesh later on. So it's a good idea if your script is not actually creating the geometry that you work with a nice watertight geometry. In this case, we're doing a grid dependency study. We're not going to be adjusting the geometry in any way. So in this case, we've spent a little bit of extra time cleaning up the geometry that we'll be using. So now I'm going to open up the script. We'll start talking about initialization. So here's the beginning of the initialization phase in the scripting process. And the first thing is loading the Glyph package. Next, we'd make a couple calls to the application class, just basically resetting Pointwise, clearing it out. In this line, we're setting the script directory to the current working directory. After that, we would define any user-defined parameters. It's a good idea before you begin scripting to basically parameterize your problem. In this case, again, we're doing a grid dependency study, so the parameters we're looking for are those that are going to drive our grid resolution. So we have parameters that drive the surface mesh resolution. Globe space 1 would control the grid point spacing on the aircraft body. Globe space 2 will be used when we actually begin refining the mesh, like on the wings and the tail. These parameters would drive the resolution of our boundary layer, and these parameters would control the grid resolution in the far field. So you can imagine these are the parameters that we have control over to actually build our family of grids. Next is when you would either define or source any procedures. A procedure is basically a function in Tcl. If you find yourself doing something a lot in Glyph, like just for example creating connectors, if you're doing this a lot, it's a good idea to write a procedure for it. So we've written this procs.glyph script that I'll just open up over here. And you can see that our very first procedure basically makes 2-point connectors from a begin point, an end point, and an average grid point spacing. We also have procedures for making unstructured domains. We have procedures kind of help us organize a little bit. This procedure, DOM from quilt, will return a domain from a given quilt. We'll be using this procedure when we actually start to modify the mesh itself. And we even have procedures for creating the far field domains. This procedure creates a couple of hemispherical far field domains. So again, if you find yourself doing something a lot in Glyph, just write a procedure for it. It makes your code a lot easier to read, and it makes it easier to debug as well. All right, so now we're into the main part of the script. So we'd call the application class method load to actually load the geometry, update the display so the changes can be seen by the user. And then we'd start setting up any defaults like connector, domain, or block defaults. So we're calling the connector class method set calculate dimension spacing. In this case, we're setting it to globe space 1. So basically, any instances of this connector class or any connector objects that are created will have this average grid point spacing. We do the same thing for unstructured domains by setting a default boundary decay of 0.85. Then any unstructured domain objects that are created will have this default boundary decay specified. All right, back in Pointwise, the next step is surface meshing. So surface meshing in this case, we would select the model, apply a uniform unstructured surface mesh to that model, and then we would go about modifying it. Now when we apply the surface mesh, we can feed it several options. One of them that we're going to tell it to do is to join connectors with an angle of 30. This basically reduces the complexity of the surface mesh. It reduces the number of connectors that are created, thus the connectors that we have to go and modify and refine in the future. So you can see there's a uniform unstructured surface mesh on the aircraft. And those of you familiar with Pointwise know that if you select a model and apply the surface mesh to the model, that each quilt within the model gets its own domain. And this is some key information that we're going to need when we actually begin refining the mesh. So back to the script. Like I mentioned, the first thing we would do is we would select the model. So we need to be able to retrieve that model. So we just call the database class method getAll to retrieve all database objects. And then using a simple tickle for each loop, we could loop through all database objects, get their description, and if it's of type model, we would just store it in the variable db model. And we know there's only one model in this case, so this variable db model will contain the aircraft model itself. Next, we would get the quilts for this model and just store them in the list db quilts. So now we have the variable db model that contains the aircraft model, and we have the list db quilts that contains all the quilts within that model. So now we can actually start surface meshing. Glyph offers a couple of methods for doing some basic error checking, and one of them that we can use is base for domain unstructured. And when we call this method, what it's going to do is it's going to check to see if the model is even meshable. If it's not, we'll just put a message. We can put a message to the Pointwise message window, and then just exit the script and try and troubleshoot, figure out exactly why the model couldn't be meshed. If it can be, we can call the database or the domain unstructured class create on database. We can feed it some options like join connectors at an angle of 30. We can even tell it to reject any unused surfaces. So if any of the surfaces in the model can't be meshed, this variable will be populated with those surfaces, and we can actually use this to do some more error checking. We can check the contents of that variable, and if for some reason a surface wasn't meshed, we could just exit the script and figure out what surface wasn't meshed and why. All right, now this is an automated process, which means that when we apply these unstructured surface domains, we kind of lose track of the domains and the connectors. We're not explicitly creating the connectors and domains. So a step, and actually an important step in the scripting process that we need to take, is we need to go and organize and try to figure out where domains are located and where their connectors are, so we can begin to modify and refine them. So the way we do this is we create an array called model DOMs, and the purpose of this array is to actually map each domain to its quilt. We know the names of the quilts, we know where they're located, so if we could map the domains to the quilts, then we'd know where the domains are. So we do this using a procedure called DOM from quilt, and this procedure basically returns the domain from a given quilt. So now we have this array that maps the domains to the quilts, so we know where they all are. We do a similar thing for the connectors. We would create some connector lists and use the procedure cons from DOM, and this would basically return the connectors from the domains. So now we know where all the domains are and where all the connectors are, and we can actually begin to modify the surface mesh. All right, back in Pointwise, that's what we'll do. We'll begin modifying the surface mesh. What it's going to do is it's going to begin refining the connectors on the wing and the tail. Zoom in here when it's done. All right, so you can see it's increased the number of points on all the connectors, like on the tail and the wing. It's actually also increased the maximum edge length of the triangles on the interior of the domain, basically reducing the cell count, especially in areas where the surface curvature isn't too dramatic. So back in Pointwise, or in Glyph, Pointwise offers a couple utilities for improving the performance of your scripts, and one of them is called a collection. A collection is basically just a group of similar objects that you're going to apply attributes to. So we create a collection of the wing and the tail domains and just add those objects to that collection. And then we can apply the unstructured solver attribute edge maximum length with globe space 1, which is 10 inches. And then when we're done, just to clean up, we would delete the collection. So we're not actually deleting the domain objects, we're just deleting the collection. We do the same thing for the connectors. We could create a collection of the wing and the tail connectors, just add those connector objects to the collection, and then we can call the method set calculate dimension spacing. In this case, we're setting it to globe space 2, which is 4 inches. We're refining it, and then call the method calculate dimension to redimension the connectors, and then delete the collection when we're done. Now that we're beginning to actually modify and refine specific connectors, we need to do an additional step. We need to organize the connectors based on their location. So we actually need to retrieve connectors like at the root, at the tip, along the leading edge and the trailing edge. So this block of code basically goes and retrieves those very specific connectors that we're going to begin to modify. All right, so the next step is we're going to start modifying the root and the tip connectors. So for the tip, it's basically just going to add more points to the connectors, increase their dimension to better resolve that tip curvature. The idea here is to better capture the geometry. At the root, it's going to actually replace the default hyperbolic tangent distribution function with a different distribution function that allows us to more precisely control the clustering at the beginning and end of the connector. As you can see, we've now clustered points towards the leading edge to capture that leading edge curvature, as well as at the trailing edge. Zooming into the tip here, you can see we've added more points to these connectors to better resolve that geometry. So back in the script. So the second utility that Pointwise offers to improve the performance of your scripts is called a mode. And a mode is basically a sandbox that allows you to modify entities or objects in a temporary state, and the actions aren't applied until the mode is ended. Now, you can also create objects within a mode, and Pointwise won't do any duplicate checking until the mode is ended. And for large grids, this could actually be a computationally intensive task. So using both collections and modes could actually significantly improve the performance of your scripts. So here we create a connector modification mode for the root connectors. Basically loop through these connector objects, replace their distribution. In this case, we're replacing their default hyperbolic tangent distribution function with a growth type distribution function. Once we have this distribution object, we can begin to apply methods to this object, mainly set its begin spacing, set its end spacing. In this case, we're setting its layers and rate, so we would set its growth rate and the number of layers. And again, the idea is to more precisely control the clustering at the beginning and end points of this connector to better resolve the geometry. So once we're done modifying that distribution object, we would take the original connector object and apply an optimum dimension to that connector based on its current distribution. In this case, we would use the method set dimension from distribution to do this. And then, like I mentioned, when we're done, we would end the mode. For the tip connectors, we create a collection of these tip connectors, add those connector objects to the collection, and then call the method set dimension from spacing to refine the connectors. And then when we're done, we would just delete the collection. Next, we're going to begin to resolve the actual curvature of the wing at the leading edge and the geometry at the trailing edge. The way this is going to work is it's going to take those connectors and it's going to replace their distribution function with a growth type such that we can cluster points towards the root and the tip to better match the spacing there so we don't have large jumps in cell sizes. But it's also going to use a tool that we have called 2D T-Rex to resolve the geometry using anisotropic triangles. So you'll see that in just a second. It just takes a little bit to run. Okay, so if I zoom in here to the tip, you can see that we've clustered more points towards the tip to better match the spacing there, so we don't have such large jumps in cell sizes. And we did the same thing at the root. So I'm not going to show that part in the script because it's pretty much the same way that we handled the root connectors by replacing their distribution function and setting the begin and end spacings. But one thing that you do notice here is that we've used 2D T-Rex to resolve this geometry. So if I rotate around here slowly, you can see that we've done a much better job of capturing that curvature on the leading edge of the tail using these anisotropic triangles. So going back to the script, we'll talk about the 2D T-Rex. So the first thing we do is we create a collection of the wing domains, add those domain objects to the collection, and then call the method set unstructured solver attribute. In this case, we're setting some T-Rex attributes, mainly the T-Rex maximum layers and T-Rex growth rate. Because it's a solver, we need to set up some boundary conditions. So we create a T-Rex boundary condition object and then start calling the methods for this object. Like set name, we can set the name of the boundary condition. Set type allows us to set the boundary condition type. In this case, we're setting it to wall because we'd like to grow away from them. Set spacing allows us to specify the initial spacing, and then apply allows us to actually add connectors to this boundary condition object. So when we're done setting up the boundary condition for the T-Rex solver, we can take the wing domains collection and initialize them. And then when we're done, we would just delete the collection. Alright, next it's just going to go through, finish modifying the mesh. It's going to improve the resolution here at the tail. You can see, again, the idea here is to better capture that geometry. So the next step in the scripting process is the generation of the boundary layer. So this script is just going to run 2 layers. It takes a few minutes to run them all, so I'm just going to open up the completed version of the mesh to show you what it does. Zoom in here, you can see that it's extruded these layers of prisms off the surface mesh. The idea here is that you would select the surface mesh of the aircraft as the face of the extrusion, then you'd march away these layers of prisms, and it would be constrained to that symmetry plane. So going back. Okay, so like I mentioned, what we would do is we would create an unstructured face object. We would create it from domains. This section of code basically retrieves all the unstructured surface domains for the aircraft. So we're just creating this unstructured face from the domains on the aircraft. Next, we would create a block extruded object that we're calling conveniently prism block. We would begin the extrusion solver mode, set up any boundary conditions for this prism block, and then per the AIAA requirements, they'd like us to grow 2 layers at a constant delta S, so that's what this section of code does. We would use the normal initial step size that we specified, and then just a growth rate of 1, and then just run it for 2 layers. The remainder of the code will run it the rest of the layers at our specified growth rate of 1.12. And then when we're done, we would just end the mode. Next is going to create the far field. This is pretty quick. I'll just zoom out here, rotate around, and you can see it's created a couple of hemispherical domains. I've turned off the interior line so the airplane is still easy to see, but it's created those hemispherical domains and created the symmetry plane. It's also constructed the final block, the unstructured block, and initialized it with isotropic tets. So creating those far field domains, we just use the procedure that I mentioned early on. This procedure creates those 2 hemispherical far field domains based on the diameter. In this case, the diameter is a function of the reference chord length of the aircraft. We feed it the center point of that sphere, as well as the spacing value, the grid spacing value in the far field. This section of the code creates the symmetry plane. The symmetry plane actually consists of a couple of edges. It has an interior edge. So you could imagine the symmetry plane being an unstructured domain with a hole in it. So basically this block of code retrieves those two edges. The outer edge is the connectors for those far-field domains, and the inner edge is the group of connectors at the extent of that boundary layer extrusion on the symmetry plane. So once we have those two edges, we could construct the unstructured symmetry plane domain. Creating the far-field block is also pretty straightforward. We would just call the class block unstructured, create the unstructured block object. In this case, we're creating it from domains. It's a single-face block where the domains are those at the extent of the extrusion, the symmetry plane domain, and the far-field domains. And once we have this unstructured block object, we would just initialize it. Back in Pointwise, the last thing we need to do is just export it to the solver. So just continue, and I'll just show you. The aircraft has been set up to type wall. Symmetry plane is of type symmetry plane, and the far field is of type far field. And it's set to export to CGNS. In Glyph, we would just make a call to the application class using the method setCASolver. In this case, we're setting it to CGNS. But Pointwise does export to over 30 different solvers, so you could select any of those. If your solver isn't supported, we have a plugin API that actually allows you to write your own custom exporter. After setting up the solver, we would set up the boundary conditions almost in the same way we set up the ones for the 2D T-Rex solver, except in this case we're just creating a regular boundary condition object. Then we would call the methods on this object, like set name. We could actually set the name of the boundary condition. This is where we would call the method set physical type to set the actual physical boundary condition type. In this case we're setting it to wall, and then add the domains to this boundary condition. So each solver has its own physical boundary condition types, and if you're not sure what they are, you can call the method get physical types, and it'll return all the physical boundary condition types that you can specify. We would set up the rest of the boundary conditions, and in this case even set up, create a volume condition object with a physical type of fluid. So in the end, the script that you'll be able to download takes approximately 8 to 10 minutes to run, generates roughly 6 million cells, 5 million of which are prisms and 1 million of which are tets. So this would correspond roughly to the coarse grid in the family of grids. So with that, I'm going to pass the mic back over to Chris, and he's going to summarize what we talked about and discuss our upcoming user group meeting in November. So Chris?
All right, thanks everyone for your attention and your time today. Along with the recording of this webinar, you'll be able to download the script and the geometry that Travis was just showing you. If you have any questions at all about the details of that script or the geometry, feel free to give Travis and I a call or send us an email. Here's our contact information. We receive the emails directly from the sales@pointwise.com alias. So we'd like to talk to you about what we showed you today, or maybe how we can help you out with your own applications and how this can be applied to those. Travis mentioned our user group meeting, so that's coming up pretty soon, in about a month, November 8th and 9th. The big thing at our user group meeting this year will be using Pointwise version 17 in the training. We have a one-day training, which is going to use, like I mentioned, version 17. And version 17 is a big deal for us because this will be the very first version of Pointwise that has all the capabilities and more that GridGen has. So anyways, it'll be the training on version 17 worth it at least to come to the user group meeting. The other big one is talks and presentations by CFD experts from our customers and clients from around the world. We'll have our distributors there this year as well. So, and as well as having direct access to the Pointwise employees. And you can register at our website at www.pointwise.com/UGM. So again, thanks for your time, and we look forward to hearing from you soon.